So I think it's time to start the last lecture of the day, to be presented by Professor McMullen from Harvard University. Because we all know that he got the Blue Medal in 1998 and the Fallen Prize in 1991. And please, the floor is yours.
Thank you. Well, it's a real pleasure to be back at the Institute for Advanced Study and an honor to be part of the Abel Symposium. Since I don't know who the Abel recipient is this year, I decided to talk instead on the work of Abel. And so there's two meanings to the word after. So after means, following the work of or explaining the work of, but I also mean subsequent to. So Abel proved his theorem on insolvability of the quintic in 1824, so more than 200 years ago. And so I'm going to touch very briefly on three stories involving three different results of Abel and some current open questions and a little bit of what came in between. So let's start with the theory of solving polynomials. I won't have time to go through all the attributions, so I will briefly flash some names here. Ruffini, who was precursor to Abel's proof, Galois, of course, Hilbert, we'll see at the end, Klein, Arnold, Smale, etc. So when we address the problem of solving a polynomial in one variable, and here I mean the most basic question of finding a formula for a root where the polynomial has complex coefficients, AI, a single formula that works for typical complex values of the AI. It raises several questions before we even begin studying the problem. So one is, what does it mean to find a root? And I think one of the main issues in trying to find a formula or find a procedure to find a root is it's going to have to break the symmetry of the polynomial. The polynomial doesn't privilege one root over another by itself. But perhaps your formula will, or your algorithm will. And if you are indeed using an algorithm, how reliable is it? So here's a quick review. Since Karen went back to the Greeks, so I'll go back to these Babylonian cuneiform texts. They apparently knew how to solve quadratic polynomials. I can't vouch for it myself. These are some snippets from the work of the Italians, Cardano, Ferrari, Tartaglia in the 1500s, where they solved the cubic and quartic equations. And then, of course, there's the famous proof by Abel. It's sort of in the function field case. It says there's no general formula for solving fifth degree polynomials, or of course, polynomials of any higher degree. And what did Abel mean by that? Well, first, let's take a look at his paper. His paper was self-published, which means he paid a publisher to print it. It's very terse. And it says Christiania here, which I learned in the course of studying Abel's work, that this is actually Oslo today. So this dates back to the Danish coupling with Norway. And in this paper, Abel has to do several things. One thing he does is he defines the notion of a formula, or we would probably say today an algorithm, very precisely and recursively, which means that his argument, which is extremely terse, has an implicit inductive element, which is often left to the reader. But one of his main results is he shows that if you have a general formula, then all the irrationalities involved can actually be expressed as rational functions of the roots of the polynomial. And that was the main insight which allowed him to complete the proof. Ruffini did not have that step. And so he proved there is no formula for solving a typical quintic by radicals. Now, this begs the question of how do you find the radical of a number? That is, we consider it somehow trivial to find radicals, but does anyone learn anymore how to compute this number of two? Yes? Okay, so at least one person knows. So one method, which works very well, is if you had the square root of 2, if it were x, then x and 2 over x would be the same. They would both be the square root of 2. So one thing you can do is you guess the square root of 2, and then you take the average between these two values, and that's an improved guess. So even if you start with 1 as your alleged square root of 2, you very quickly converge to a very accurate root of 2. In fact, the number of digits of accuracy doubles with each iteration. And what is this procedure? It's an instance of what we now call Newton's method. So Newton's method, I'll remind you, let's do an example for a cubic. You guess a location for a root of your polynomial. Here's a root where it crosses the real axis. You go up to the graph and you see you're not on the real axis, on the x-axis. So you draw the tangent, you see where it crosses the real axis. That's a better guess for the root. And then you just repeat this procedure and hope for the best. Okay, so in fact, Newton's method is reliable for computing radicals of any degree, nth roots of polynomials, but it's not so easy to predict from the initial guess which of the 3 roots of this cubic you're going to converge to. And so this question was examined, in fact, by Cayley. I have this quote from Sternberg here. I won't go into details, but look at that puzzled look on his face. So he could not figure out how the complex plane is partitioned into various regions which converge to each of the different cube roots of unity. Now we now know how to experimentally solve that problem, and this is why he couldn't figure it out. So there's a root, a cube root of 2 here, here, and here. And if you're in this red region, you converge to the root, the real root, and here you converge to one of the 2 complex conjugate roots. And so very roughly speaking, the plane is divided into these 3 sectors. But then you can see there's a region over here which actually maps to the red. So you can start with a negative real number and you converge to the positive real cube root of 2. Also, there's a fractal region where if you happen to land exactly on one of the boundary points between these different regions, you wouldn't converge to a root at all. But there's 0 probability of that happening. And so this procedure is in fact reliable for computing the cube root of 2. And in fact, Newton's method in general for computing nth roots gives a picture that's very similar to this one. Okay, but what about this cubic? So if we change the cubic, this cubic has, I've drawn it backwards, I think, but it has 1 real root and then 2 complex roots. So if you start iterating in the wrong part of the real axis, you may not converge to a root at all. That's what's happening. That's what's happening here. And so I've colored the regions according to which root you converge to, but there's also a small blue region here where you don't converge to any root at all. So this method, Newton's method, is actually unreliable for general cubics in the sense that there's a positive probability you choose a bad initial guess. And it was in this context that Steve Smale, in his program for numerical complexity theory, began asking if there is a simple formula like Newton's method for solving polynomials of degree 3, 4, 5, etc., that is, to the contrary, reliable. It doesn't have any of these blue regions. Now, this is a blow up of the blue region, so you can see it's fairly complicated. There's another thing you can try. It turns out that the worst initial guess for the cubic is its point of inflection. And so you can ask, if you iterate the point of inflection, which root of the cubic do you converge to? So this is a picture of the space of cubics. And the colors indicate which root the point of inflection converges to. And everything looks good because you see only these three colors, except there's some sort of little almond-like decorations, which we might hope to ignore. But if we blow up one of these, we see a white region where you're not converging to any one of the three roots. And in fact, it's a slightly distorted copy of the famous Mandelbrot set. So the whole rich bifurcation theory of quadratic polynomials is also present inside of Newton's method once you try to solve polynomials that are more complicated than x to the n minus a. Now, this breakdown of Newton's method is necessary. It's implied by a rigidity theorem, which can be stated in the following way. If you have a reliable iterative algorithm, then all the rational maps that occur are intrinsically the same rational map. That is, up to a change of coordinates on the Riemann sphere, up to conjugation, by a Mobius transformation, there is only one dynamical system. And so in modern language, we would say the family of rational maps is isotrivial, and indeed, this is related to, in spirit, to Mordell's conjecture for the function field case, although it's much simpler. The proof uses a rigidity theorem due to Thurston. Here's an instance. I mentioned Newton's is reliable, for example, for quadratic polynomials. And in fact, Cayley was able to figure out how Newton's method works for quadratics. Here's the two roots of a quadratic polynomial. And which root you converge to? The closest root. So these are the points that are closer to this root. This pink region all converges here. This blue region all converges here. And you can see that the whole picture is kind of Mobius invariant. In fact, if we move the two roots to 0 and infinity, it turns out the dynamical system is simply z goes to z squared. So we have z goes to z squared acting on the sphere. And one way to build Newton's method for quadratics is you just pick up 0 and infinity, you put them at your two roots, and then you iterate the resulting rational map. Now you might object, I don't know where the two roots are. But you see, z goes to z squared is symmetric under interchanging the roots. So in fact, when you do that, the rational map you get only depends on symmetric combinations of the roots. And so that is a way you might have discovered the Newton's method for quadratics. By the same token, this rigidity theorem implies there is no reasonable way in this very restrictive setting, iterating one rational map that depends algebraically on the polynomial, there is no way to solve polynomials of degree 4 or more. And the reason is the attractor of such an algorithm would be the four roots of the polynomial. They have a non-trivial cross ratio. So you can't use the same dynamical system for all polynomials because they have different cross ratios, and so they cannot be Mobius conjugate to one another. So if you have to, as soon as you start to deform the rational map, it's forced to break and bifurcate for some particular polynomial. So degree 4 is already out, which leaves open the question of what happens in degree 3. And the answer is, in fact, we can find a rational map with S3 symmetry. The z squared had S2 symmetry, the symmetric group on two elements. Here's a rational map with a attractor at 3 points. Every point on the sphere, with a measure 0 exception, converges to one of those 3 special attracting points. And the whole picture is symmetric with respect to the action of S3 by Mobius transformations on the sphere. And so once you've found this map, you can use it to construct a method for cubic polynomials. And here's an explicit formula for this map. And the formula we get for cubics is the following. In fact, if we impose some mild conditions on the map, it's unique. And to solve the polynomial x cubed plus ax plus b, it's given by this formula you might not have thought of. Now, when I presented this formula in a lecture, John Tate told me the next day that I had just written down Newton's method. And I thought, really? And he said, yes. In fact, this is Newton's method for your original polynomial, but you know, there are also rational functions that also have these as their zeros. And you take this polynomial and you divide by this quadratic polynomial, and then Newton's method applied to this much easier to remember function is in fact the formula that I've written down here. Okay, so what we see is that in this fairly constrained setting, one can solve polynomials of degree 2 and 3, but one cannot find roots of polynomials of degree 4 by a single iterative procedure. Okay, now why doesn't that contradict the existence of formulas for solution by radicals? It's because when you solve a polynomial by radicals, say of degree 4, you extract more than one radical. And what that means is to put that kind of procedure into this setting, you don't just iterate one function. You iterate one function to find one of the radicals, you take that result and then perhaps some rational function of it with the coefficients of the polynomial, plug that into a new algorithm. Take that result, plug it into a new algorithm, and then at the very end of the day, out comes a root of the polynomial. So we want to take these iterative procedures and think of them as subroutines that can be nested or called recursively. And that gives us a domain of, so to speak, algorithmic computation, which is certainly strong enough to solve fourth degree polynomials by the usual formulas. So that's the idea of a tower of algorithms. And how powerful are these algorithms? Well, it turns out that one can show that a field extension, and here I'm going to just state this result kind of vaguely, a field extension, this is in the function field setting, can be computed by a tower of these purely iterative algorithms if and only if its Galois group is within A5 of solvable. A5 is the smallest simple group, and other than the Z mod P's, sorry, the abelian simple group. And so you have to be able to decompose the group into cyclic groups or A5. And Peter Doyle and I collaborated in proving this theorem. And the reason A5 appears, of course, is that because of the Platonic solids, these are the most interesting groups which act by Mobius transformations on the Riemann sphere. So if you can reduce the monodromy group for your polynomial from S5 to A5, then you can solve the quintic. And of course, you can do that reduction by adjoining the square root of the discriminant. But you can't do a general 6th degree polynomial because you can't implement the symmetries A6 as symmetries of the Riemann sphere.
What does this up to A5 mean? The Rodin-Hölder series of the group?
Yes, that's right. So exactly. Exactly. So the successive quotients are either cyclic or
But what happens when the roots are complex? I haven't, you're finding real roots.
No, sorry.
Oh,
That's
what
red herring. All my pictures since the beginning have been in the complex plane.
Okay.
This is my only real picture. And the real numbers have measure 0. And so this unfortunate behavior,
Yeah.
well, it turns out in this case, it persists into the complex plane. But for extracting nth roots, it's fine. So everything here is over C. Any other questions at this point?
How did Tate figure that out?
By hand.
What is the explanation of the denominator?
Ah, That's a very good question. So, not that your question wasn't good also. I didn't mind Meldreth Tate at the time. So you might ask, if I have 3 points on the sphere, that's what it takes to define the cubic, where do I get the 2 zeros of this auxiliary quadratic? Here's the intrinsic definition. There is a unique Mobius transformation that cyclically permutes these 3 roots, and it has 2 fixed points. Those are the zeros of the quadratic. Okay, so so we can do degree 5, we can't do degree 6. What is the state of the art? So as I say, this result shows the quintic can be solved, but the sextic cannot. Oh, I should say, in fact, we have actual formulas for solving the quintic. And as you would guess, they rely on iterated rational maps whose symmetries are the symmetries of the icosahedron. And it turns out that if you give me any n points on the sphere, there is a canonical rational map of degree n minus 1. And if those n points are symmetric, this rational map inherits the symmetries of those points. So if you take the 12 vertices of an icosahedron, they canonically determine this degree 11 fractal soccer ball, which shows the dynamics of a rational map with A5 symmetry. And similarly for the edge midpoints, there's a degree 19 map, and for the faces, the 30 faces, there's a degree 29 map. We use the degree 11 map in writing down an explicit iterative algorithm. Okay, so the frontier is degree 6. And I want to conclude with an open problem about degree 6, but it's not my problem. Let me say the problem first. So what we've been doing is we've been taking some number, like our initial guess, we've been running it through an algorithm, and what comes out at the end of the day is an algebraic function of z. In other words, a multi-valued function that satisfies an algebraic relation with respect to the original number z. And it's a function of one complex variable, because we're doing all of our iteration in one variable. We're taking limits in the complex plane. So here's a basic question. Can polynomials of degree 6 be solved using algebraic functions of just one variable? So forget about what the algorithm is. Let's just focus on the fact that whatever it does, it produces an algebraic function. So this turns out to be known as Hilbert's 13th problem. And it's unsolved, and I encourage people to think about it because it's widely regarded to have already been solved. So there's not too much of a crowd around it. But it was
a small crowd around you.
It was solved by Arnold in collaboration with Kolmogorov, but they solved it in the case of continuous functions rather than in the case of algebraic functions. And so let me just remind you what Klein showed for the quintic is the following. There's a degree 60 map of the Riemann sphere to itself, which takes the quotient by A5. And if you can invert that map, that's a one variable algebraic function. If you add that to your stockpile of things you can compute in addition to radicals, then you can solve the quintic equation. So in degree 5, Klein found long ago a very explicit algebraic function, which can be used to solve quintic equations. And for degree 6, there is no corresponding function, and I think it's widely believed not to exist. And to put differently, if you take the polynomial x to the 6th plus, let's say ax squared plus bx plus 1, the roots of this polynomial are somehow essentially two variable functions of these coefficients a and b. They cannot be expressed as compositions of algebraic functions of one variable. So it's really a fundamental problem. Are there functions of two variables that are not compositions of functions of one variable plus, of course, addition and multiplication? So this is open and it's been revisited by many people: Arnold, Heisuke Hironaka, Benson Farr, Mark Kissen, Jesse Wolfson. However, none of these works has made progress on this question. They've circled around it and they've developed a very rich theory of simplifying problems down to smaller and smaller number of variables. But as usual, in complexity theory, the problem is lower bounds on the complexity of the solution, and essentially no progress has been made on the problem of lower bounds. Okay, so there is an arc that begins with Abel's work of 1824 and ends with a famous problem that's still open today. Okay, now I want to turn to the theory of braids. And again, there's many people whose names should be mentioned. Sorry, I left off Artin and many other people. I'm going to go in a direction related to Schwartz, Picard, Levasseur, Laricella, the work of Deline and Mostow, the work of Thurston, and many others. Okay, but first let me look at the corresponding paper by Abel. So this paper, 1826, it's devoted to studying integrals, a very large class of transcendental functions. So the typical transcendental function considered here is something like one is given a polynomial, say you even know the roots of the polynomial this time, it has nth roots. You take the algebraic function, which is its dth root, perhaps you multiply by a polynomial in x, and then you try to integrate this function. And you might consider definite integrals, you might consider indefinite integrals, and indeed Abel goes beyond this, even this kind of integral. I just wrote it down for concreteness to consider quite general integrals of what we would now say, from a modern perspective, are the integrals of one forms on a compact Riemann surface. So the modern perspective would work like this. Instead of putting in a radical, you introduce a new variable, y to the d, which is one which can satisfy all of the possible choices for a dth root of this polynomial. This defines a compact Riemann surface. The integrand for suitable I and j, and I'm here allowing you to raise y to a power, defines a holomorphic one form, i.e. an element of h10 of x. So it sits inside the cohomology of this compact Riemann surface. And then one might consider definite integrals, say along cycles on this surface, and one is eventually led to the theory of the Jacobian, which is the way to capture the holomorphic function on x you get by simultaneously integrating all g of its independent holomorphic one form. So the result is a complex torus, and it plays a central role in the Abel-Jacobi theorem, which predicts what divisors are principal divisors. So the whole modern theory of transcendental algebraic geometry, at least in the case of curves, is implicit or explicit in this seminal paper of Abel. Now, the one thing Abel doesn't consider, as far as I can tell, which is a slightly more modern perspective, is once you have all this big package, what about varying these roots, b1 up to bn, without allowing the polynomial to acquire multiple roots? So what about allowing these roots to move around in the complex plane without collision? That's the notion of braiding. So we have an x that's defined by this equation, and this x comes equipped with a symmetry because you can multiply the value of y by an arbitrary dth root of unity. So there's an action of z mod d on this Riemann surface. It's not a typical Riemann surface. It's one with a special symmetry group. Let's keep in mind that symmetry is part of the data as well as the map to the projective line given by the coordinate x. Then, for any dth root of unity, we get a representation of the braid group. Namely, the braid group goes into the automorphism group of the first homology of this surface x. And then, since since as we move these points, the action of T goes along for the ride, we can even restrict this automorphism of H1, this is H1 with complex coefficients, to the qth eigenspace, that is the one where T acts by multiplication by this particular qth root of unity. Okay, so recapitulating, if you have endpoints in the plane, they give rise to this complex vector space, H1 of X. We also have this cyclic action, which allows us to look at the qth root of unity part. And as the points move around and come back to one another, we can follow this vector space along as well as this one. It returns to itself by some linear map respecting, for example, the intersection pairing on H1 of X. Okay, so here's just a picture of what a typical braid means. And this is a procedure by which one can get these interesting linear representations of the braid group, which is a fortiori a purely topological object. Now, in fact, I haven't used the Hodge structure at all here. I didn't say anything about holomorphic one forms or stuff like that. This representation is pure topology. I'm just using ordinary H1 here. You could say I'm taking the branch cover of the two sphere branched over n points and the topological braid group acts, etc. And this family of representations are known as the Barrow representations of the braid group. One usually takes Q to be a free variable, then an indeterminate. I'm specializing it to a root of unity. So this is, I think, quite remarkable already that one gets linear representations of the braid group more or less out of polynomials and d roots, and very much in the spirit of Abel's paper. Now, I want to remind you that on H1 of X, say with complex coefficients, we have a Hermitian form, I over 2, the integral of alpha wedge beta bar gives a Hermitian form on the space of on the entire one-dimensional de Rham homology with complex coefficients. And I'm just recapitulating what I wrote down before. That form, which I've written here, it has signature GG when restricted to all of H1. It has G positive directions and G negative directions. The space is 2G dimensional. But on this particular eigenspace, it has some other signature, RS. So it's desirable to know what the signature is of this sub-representation. See, this representation is highly reducible because it commutes with T. So we're restricting ourselves to this simpler piece and we get more interesting signatures that way. So there's a neat algorithm to figure out what the signature of this form is. Namely, if you have, say, 6 points, you make 6 dots on the circle. And then when you pick your qth root of unity, remember your qth root of unity involves D. The dots only involve N. So D could be very large, and the K could also be very large. So you get some sort of, any root of unity on the circle will do. And you draw a straight line from 1 to the qth root of unity of interest, and you see a certain number of dots above the line and a certain number below. That's the signature. So for this qth root of unity, it's signature RS, where R is 3 and S is equal to 2. And if you happen to go straight through one of these dots, you get the signatures I've shown here. For example, this is 4, 0, because you ignore these 2 dots, and then you have 4 below the line through these. Okay, so it's easy to figure out what these signatures are. And what you see is the signature, as Q increases, it starts out being positive definite, then it becomes Lorentzian, then it goes through some higher rank stuff, and then eventually it becomes negative definite. So different values of Q give different flavors of representations. Okay, let's look at 2 of those representations, but I want to add one more element to the picture, which will use Hodge theory. Namely, for any particular root of unity, we can associate to it a holomorphic one form on our surface X. And now I really am using Hodge theory. So I take the form dx over y to the k. And Q is chosen, so this holomorphic form lies in H1 of X with coefficients in Q. The integral of a holomorphic form, wedge its complex conjugate, is positive. So it gives you a positive line in this space of with a possibly indefinite Hermitian form on it. And in view of that choice of positive line, which now depends on exactly where the BIs are, we get a map from the moduli space of n points on the sphere, or at least locally we get such a map, into what I'll call HRS, which is just the space of positive lines in a complex vector space of signature RS. So for example, HR0 is just the complex projective plane of dimension r minus 1. H1s is a model for complex hyperbolic space. So remarkably, once we start really looking at the Hodge theory rather than just the topology, we get a map from this well-studied moduli space, a very simple space describing n tuples of points in the plane up to automorphisms of C. We get charts into, for example, the projective plane or into the complex hyperbolic space, in both cases preserving natural metrics coming from the intersection pair. So what does that additional data provide us with besides this representation for the braid group? Well, let's first look at the case of definite signature. So when the signature happens to be positive definite, we get algebraic integrals out of this construction. So let me just explain that with a concrete example. If you take y to the fourth is equal to a certain degree 4 polynomial in X, we know where the roots are, that corresponds to this line. There's 2 dots below the real axis. That means RS is equal to 2, 0. And that means that the monodromy group of this action lies in the compact group U2. And since U is compact, and one can show the monodromy is discrete, it preserves a lattice, the monodromy of this apparently multi-valued function must be finite. And as a result, you can prove that, say, the definite integral given by integrating between 2 roots of this polynomial, the form dx over y cubed, which is invariant under multiplication by, which multiplies by zeta 4 under that particular change of variables, is an algebraic function of b1, b2, b3, and b4. Okay, so this is a philosophy that goes all the way back to Schwartz. Finite monodromy gives rise to algebraic functions. And indeed, if I simplify the formula a little by setting b1 and b2 equal to 0, 1, I have the following integral, which you could assign your calculus class, and hopefully they will be able to discover it has this simple algebraic expression. So indeed, it only involves radicals and a couple of values of the gamma function. Okay, so that's what happens when you get finite representations of the ray group out of this story. However, the most interesting thing is what happens when in the hyperbolic case, that is in signature 1s, and the discoveries here, which are quite deep, are due first to Deline and Mostow. And I'm going to, again, just give you a concrete example. But you see, you're going to get charts for moduli space into complex hyperbolic space. And indeed, you're going to be able to take some sort of completion of moduli space and turn this moduli space, which has a quite transcendental structure, and it's very far from being associated to traditional symmetric spaces. There will be some sort of completion of this moduli space, which carries a metric of constant holomorphic sectional curvature. In other words, it's a complex hyperbolic manifold. So something transcendental turns into something complex hyperbolic. It's really quite miraculous. And one of the examples, quite concretely, is if you take d equal 18, n is equal to 4, you take the 11th root of unity. You can see here there's 1 dot below and 2 above. So that implies RS is 1, 2, which means that on we get a representation of the braid group, and what we get is a complex hyperbolic manifold that's some sort of completion of the moduli space of 5 points on the sphere. Okay, now much more than that. There are other known constructions of lattices in unitary groups, but most of the known constructions use arithmetic and they provide arithmetic lattices. On the other hand, monodromy doesn't have this arithmeticity built into it. Monodromy in general, for families of varieties, may or may not produce a lattice, it may or may not produce a discrete group, but when miraculously it does, there's no reason for that group to a fortiori be arithmetic, and indeed it's not. So this is one of the first and a very remarkable example of a non-arithmetic lattice in U12, in the case Karen likes, the complex hyperbolic case. Now, I just want to say a word about what Thurston did. If you change your root of unity, it turns out you get a non-discrete group, but you still get charts on moduli space, and you get a complex hyperbolic structure on moduli space, but its metric completion is no longer an orbifold, it's what's called a cone manifold. So one of the beautiful things about Thurston's perspective is that quite uniformly, independent of what Q is, it doesn't even have to be a root of unity, you get complex hyperbolic cone manifold structures on completions of moduli space, and each one of these has its own volume. Now, one of the problems when you're producing interesting non-arithmetic groups is to know whether or not you produce the same group twice. And one thing I should have said, Thurston's development started with a 1986 math Olympiad problem, but let me move on from that. So what I want to say is that because we have associated to this non-arithmetic group both a discrete representation and an indiscrete one, and both of these representations have an associated volume, we can take the ratios of those two volumes, and that ratio is in a commensurability invariant. So it can be exploited to help classify commensurability classes of non-arithmetic groups. And let me just quickly skip to the punchline. So using these volume ratios, one finds that the 16 basic known non-arithmetic lattices arising from this moduli space construction, they fall into 10 commensurability classes. And this idea was first exploited by Capes and Muller, and in terms of Liakhmanov exponents, and I simplified it a little to use volumes. And so here's a table of the known examples. There's some combinatorial invariants that determine them. And these are the volume ratios. They're always rational numbers. They're sort of like Euler characteristics. And for example, these two here have the same invariant, and in fact, they're commensurable. These are commensurable. The only accident here is that these three have the same volume invariant. These two are commensurable. This one is not in the same class, but you can pull it aside using its trace field. Okay, so this was just a glimpse of how Abel's study of these slightly more complicated calculus integrals led to the discovery of non-arithmetic lattices in unitary groups, especially in complex hyperbolic unitary groups. So what's the unsolved problem here? The unsolved problem is, can we find non-arithmetic lattices in every U1n? That is, if we look at complex hyperbolic 4 space, can we find a group that acts on this space with a finite volume quotient, but it does not arise from an arithmetic construction? The previous constructions only work in U12, well, also in U11, U12, and U13, but the frontier is U14. And just for context, Peter's left, but he mentioned Corlet's rigidity theorem. There's one knows that, for example, in complex hyperbolic space, in real hyperbolic space, especially in dimension 3, there are abundant examples of non-arithmetic lattices. And in fact, that happens in every dimension due to work of Gromov and Piatowski-Shapiro. However, when one goes to quaternionic hyperbolic space, or even more to rank 2 symmetric spaces, then rigidity takes over, and all the lattices are forced to be arithmetic. And so these complex hyperbolic cases are exactly in the middle ground. And it's really an interesting question to ask if, as this integer 4 increases, more and more rigidity ensues until finally all lattices are forced to be arithmetic. That's kind of the boundary of our knowledge of super rigidity in this setting. Okay. So the final topic, which you probably don't think Abel worked on, is the theory of billiards and polygons. And here I'm really pleased to be able to share something that has been worked on by a lot of people, some of whom are in the audience. And I'm going to exposit another algorithm of Abel's that deserves to be more widely known. So it's in this paper about integrating certain differential forms involving radicals and getting, so to speak, elementary values for the integral. However, the modern interpretation is somewhat different. That's what we're going to use. So one of the ways to describe what Abel is answering is the following. If you have 2 points on a Riemann surface, when is there difference torsion in the Jacobian variety? The Jacobian variety is a group. P minus Q is a divisor of degree 0, so it determines an element there. When is some power of it equal to 0 in this group? And I learned about this work of Abel from Dick Gross, who knows everything and sadly recently passed away. Okay, so here's what Abel studied. We consider now the very simple case of a hyperelliptic Riemann surface. So y squared is equal to some polynomial in X. The number of zeros and the genus are related by n is equal to 2g plus 2. I'll do the case where n is even for simplicity. And here's the picture you should have in mind. We pick endpoints on the projective line, and we form a Riemann surface, which is a degree 2 branch covering of the projective line branched over these endpoints. Now, it's not branched over infinity. So there are 2 points lying above the point at infinity on the downstairs on P1, 2 points where x is equal to infinity, so to speak, in this equation. And it's the difference between these points that we're going to study. Okay, so here is our problem. We've given x very explicitly, as well as p and q. When is the difference torsion? And here's what Abel proved. There's actually many equivalent statements. So the first is the difference is torsion. The second is Pell's equation, a squared minus b squared times d equals 1, has a solution. Notice how similar this is to the traditional Pell's equation you know from basic number theory, which would just be the a and b and d would be integers. This would be describing units in the ring of integers in Q adjoint square root of d. And indeed, in that case, one can analyze the existence of units by looking at the square root of d and its continued fraction expansion. There's also a continued fraction expansion for this polynomial. Namely, you write it as a polynomial. You take the square root of d and you try to write it as a polynomial. There'll be some error. And then you take the reciprocal of what's left over. So in other words, you start writing its Laurent expansion about infinity, and you see a polynomial and then some other terms. You take the reciprocal of what's left over, and you see another polynomial, and you keep going. And this difference of points is torsion exactly when this continued fraction is pre-periodic. That is when you eventually start seeing the same ANs over and over again. By the way, as usual, this does not give an algorithm to determine when it's not torsion, because you don't know how long you have to wait for the continued fraction to repeat. Nevertheless, it does give an algorithm which is extremely useful and effective in the case where you do get torsion. And Abel's interest in this was that in the case where you have torsion, you can find a polynomial f of x such that this apparently difficult looking integral can be expressed in terms of logarithms and an algebraic function of x. And finally, all of these things are equivalent to saying there is a unit in the coordinate ring of the affine part of this curve x. Okay, so this is the part of Abel's work that I think deserves to be better known. I'm just curious, how many people know about Abel's work on this type of continued fraction? Yes, okay, so Kila also knows everything.
Can I
So, yeah.
ask, when you said it's unknown how long you have to wait to get the periodic condition, are there bounds?
No. So unlike in the case so if d were an integer, there are bounds. But in this function field case, there are not.
Okay.
There are no bounds in terms of the order of torsion.
Sorry?
So the order of
That's right. So you're trying to find a function that has a 0 of order n here and a pole of order n there. And you don't know what n's going to be. So yeah, there's no a priori bounds as far as I know.
if you know the height of the bees, then there are bounds.
If you know the height of the b's, you may very well be right. So when I say, I wasn't allowing that data, but I think you're right. I mean, after all, if you control enough things, there's only finitely many examples. Yeah. Okay. So anyway, I wanted to advertise this theorem of Abel, and let me conclude with an application to billiards that I think is maybe kind of surprising. So let's shift gears for a second. So I'm going to be interested in the behavior of a standard classical mechanical idealized billiard ball bouncing off the sides of a polygon in the plane. For example, especially a regular pentagon or a regular n-gon. Those will be interesting examples. The case of a square is, of course, very well understood. A trajectory is periodic in the square if and only if its slope is a rational number. And there are, it turns out, infinitely many periodic trajectories in every regular n-gon, and much more is true and can be determined about these types of billiards. So the first thing I want to do is tell you how to look at a billiard table and associate a genus to it, and more precisely, associate to it a compact Riemann surface. So I'll just show you the genera and the polygons, and you can guess what the genus is. So these are genus 1. Those are all the regular polygons of genus 1. These are all the regular polygons of genus 2. That's 5, 8, and 10. And in fact, in general, if n is odd, then the genus is determined by writing n as 2 plus 1. And when it's even, you use one of these formulas. The genus is just what you would think it would be. Namely, for the square, you can glue this edge to this edge and this edge to this edge and obtain a torus. And the straight line flow on this flat torus is very closely related to billiards in a square. If you have an octagon, you can glue opposite edges and you'll obtain a surface of genus 2. You might think if you have a regular tengon, you could glue opposite edges and get a surface of higher genus, but it turns out to still be 2. The reason it's still 2 is that all the vertices are identified when you glue up an octagon, but for the decagon, you get 2 vertices after gluing. In any case, by taking the flat structure or the one form dz on the plane, which is invariant under translation, we not only get a Riemann surface from this billiard table, we get a holomorphic one form. So in brief, in the case of the octagon, you take this polygon in the plane plus dz, which is a holomorphic one form, and it descends to the quotient under gluing to give a holomorphic one form on a surface of genus 2. The red vertices become a single point downstairs, and that single point is the unique zero of this holomorphic one form. It's a zero of multiplicity 2. Okay, so there's a way to pass back and forth between at least very special billiard tables and compact Riemann surfaces, and indeed Riemann surfaces equipped with one forms. So I want to emphasize that here the one form has just one zero. In general, in genus 2, one form has two simple zeros. This one has a single double zero. Now, the theorem, which goes back to Veitch, is that in a regular polygon, every billiard path is either periodic, it comes back to where it started, or it's uniformly distributed. There's a very sharp dichotomy between kind of completely determinate behavior, periodic, and completely chaotic behavior. And in this case, I say that the billiard has optimal dynamics because of this sharp division. This doesn't hold for typical polygons, but it's true for these very special ones. These special ones are like rare jewels. And of course, the symmetry here, I only have countably many examples. In fact, even worse, I only know 3 examples of genus 2 if all I know about are regular polygons of 5, 8, and 10. So the problem I want to address or finish with is this: are there infinitely many optimal billiard tables in genus 2? So there's the ones we know from the work of Veitch. And the answer is, in fact, there are infinitely many, but you have to know where to look for them. And where Veitch was looking was, he was looking at Riemann surfaces that had special automorphisms. But it turns out that more generally, you should be looking at Riemann surfaces whose Jacobians have special endomorphisms. And once you shift your perspective, a la Abel, from symmetries of the surface to endomorphisms of the Jacobian and to one forms, you quite easily find that there are, in fact, infinitely many optimal tables of genus 2. So let me just, this is slightly technical, so I'll just say the words. If you build this Riemann surface and its Jacobian admits a special endomorphism, that is, its endomorphism ring tensor Q, it contains the field Q adjoin root T with omega as an eigenform, and this form has a double zero, then the associated polygon has optimal dynamics. So with this Abel-esque criterion in mind, one can find there are infinitely many optimal billiard tables in genus 2. For example, here's one of the tables associated to Q adjoin root 13. It no longer looks like a regular polygon. It's an L-shaped table, but combinatorially it has 8 edges, and when glued up, it gives a surface of genus 2 and a one form with a unique zero. Okay, now, when I first discovered this infinite family, I was imposing this condition that the one form has a single zero. And I thought, wow, look at all of these examples. When I allow the zeros to be distinct from one another, there will be this vast jungle, almost impossible to get my head around, of even more examples. And then I discovered there was only one example I could think of, which is the one coming from the regular decagon. So as I mentioned, when you glue up the sides of the regular decagon, you get 2 kinds of vertices. And as a result, this corresponding one form has 2 distinct zeros instead of just one. Does that help or hurt the existence of such tables? Well, it turns out that there's a beautiful theorem of Miller that says if you are going to have 2 distinct zeros, their difference has to be torsion in the Jacobian. And now we bring the perspective of Abel's theorem to bear. This, by the way, is a picture of what the two zeros look like in the case of the decagon. This oscillating curve here can be used to show their difference as ordered 5 in the Jacobian. In view of this additional constraint, one can make a further argument to show, in fact, every optimal billiard table of genus 2 is either one of the L-shaped tables, like the one I just showed for Q adjoint square root of 13, or the regular decagon. So indeed, in genus 2, we have a complete classification of the optimal billiard tables. Okay, and in brief, it uses Abel's perspective plus a degeneration. You let the curve of genus 2 degenerate to a rational curve by acquiring, this is a picture of the hyperelliptic curve, it acquires 2 double points and becomes rational. The points P and Q persist, but now they become torsion in the Jacobian, which is essentially C star across C star for this degeneration, which means they become roots of unity. We also have real multiplication at hand, and that implies that any example we can find with distinct zeros must be related to a quadratic field as well as a ratio of 2 values of the sine function at rational multiples of pi. So in brief, you can ask yourself, for what rational numbers, like a 12th and 5/12ths, is the ratio sine pi alpha over sine pi beta a quadratic number? And in fact, there's only 15 examples. They're all listed here. We can analyze them each by computer, and you see that only the decagon survives to actually give you a billiard table. Okay, so that's the end of this application of Abel's theorem. And once more, I want to end with an open problem. So it turns out this kind of analysis can be carried out also in genus 3 and 4. And in those higher genera, one needs to replace the Jacobian variety by the prim variety for some involution on the surface. We remain in the world of quadratic fields, and everything works, but that construction itself breaks down in genus 5. And so this, by the way, is the decagon example. Let me just end with this. Are there infinitely many optimal billiard tables of genus 5? So yet another example of the great amount of mathematics that has evolved from the work of Niels Henrik Olff.
Thank you very much for a great talk. It's open for questions or comments from the audience.
Yes.
No.
In the first topic, approximating solutions of polynomials, the algorithm we presented were one variable.
Yes.
Are the more algorithms more variables?
Yes, yes. So here's an algorithm. If you relax the condition that of a relationship between the variables and the degree, you can take the companion matrix for the polynomial, take a random vector and start iterating it. It will grow like the largest root of the polynomial. So yes, there's actually fairly easy examples when we move out of this constrained setting. So, and indeed, in all of these examples, I'm focusing on problems which interact in an interesting way with the kind of complex and transcendental algebraic geometry over C that Abel initiated. But I've just talked to someone at T, not everyone is interested in billiards and pentagons. They also would like to do convex bodies, even with smooth boundary. It's not so closely related to Riemann surfaces in that case.
Any other questions?
Also, going back to the first problem, you talked about finding roots to functions on Riemann surfaces, but what about the higher genus keys?
Say that again?
In the first problem, you talked about finding roots to functions on the Riemann surface. But what about finding solutions to functions on higher genus surfaces? If I have a torus mapping to P1? and I want to find some point optimally. What do we know about that problem?
So I'm not quite sure what the question is. If you have
Sorry.
if you have a polynomial, if you have say, an elliptic curve sitting over C, you pick a point downstairs.
And I
Then
have
to
some,
find the coordinates of the points above it is to solve a one variable polynomial.
but suppose I have some high degree polynomial in the X and Y.
Yeah.
How do I, like, what's an optimal way to find the solution by using some iterative method or something like this?
Yeah, so I mean, all I can say is cut it with a line and reduce to a polynomial.
But there's nothing-
Perhaps there are much better methods. I mean, certainly, you know, you can use the addition law on elliptic curves in a highly non-trivial way.
Any other questions?
Do you believe that every lattice in a U14 is arithmetic or not?
Well, let me just say, it doesn't matter what I believe. Key, what do you think?
Not sure.
Okay, there's Elon, he, and many other people are much more knowledgeable about this kind of arithmeticity collection. Also, Pierre, of course. Yes, he is. Thank you for the question.
Final questions? You want to say something? No. Okay, so let's thank Kurt once more for a great